Hello everyone, good morning, welcome to MOG Sundays. Today we have with us engineer Utpal Chakravarty, a civil engineering graduate from Assam Engineering College. He led landmark bridge projects here in Goa, including the Mandovi and the Zuari Cable-Stayed Bridges. Alongside engineering, he also cultivated a passion for construction photography and documenting intricate process of bridge making with precision. Since retiring in 2025, he has fully dedicated himself to his photography. The Zuari Cable-Stayed Bridge in Goa is one of India's most striking modern bridges, linking both North and South Goa across the Zuari River. Its creation was a journey of engineering skill and teamwork, and Utpal has captured this beautifully through photographs at every single stage, so he'll be taking us through them today. I now welcome Utpal Chakravarty to take us through the making of the Zuari Bridge. And I request everybody to put their phones on it so that we know to do them.
Thank you so much. Thank you for the nice introduction. And good morning to everyone here. In this rainy weather, all of you could come. So thank you so much. Otherwise, I would have, some time back, maybe 15 minutes back, I was thinking I will be talking to my wife all the while, and she has already seen this so many times. Thank you for coming here. So we'll start with the bridge of this particular Zuari Cable-Stayed Bridge. Is it enough sound? Okay. Or without this, is it okay?
No. Yes.
Anyway, so this bridge is, as the name suggests, it's a cable-stayed bridge. So people say, some people, they even refer it as a hanging bridge. Have you heard somebody calling this sort of cable bridges as hanging bridge? Yeah, but in engineering term, there is nothing called hanging bridge, okay? With cables, we normally construct only two types of bridges. One is this cable stay, and the other one is your suspension cable bridge. So these two types, but we never refer it, as an engineer, we never refer it as a hanging bridge. So now Goa has another three such cable stay bridge. Have we, all of us know about it and we have seen it?
One more we know.
Mandovi, you know. Then there are two more. Aldona is the one. That was the first one, it was done in 2004, the first EFI, when it happened. That time it was open. So I will just show you quickly those two pictures also. So this is Aldona, okay? This is about 235 meter length with some 105 meters of that navigational span in one side on the right. Then, of course, this is Mandovi. So, fortunately, I was also present in this project from beginning. So this is Mandovi. Then it was opened in 2019. And here this cable stay part is 620 meters. Whereas the bridge I'm going to talk about is 640 meters. And the third one, other than this bridge, this is in, Sada to Varnapuri, there. So it is in Vasco. Yeah. So, but this bridge is not mainly for the local traffic, it's mostly for the port. So this way they are going to, actually they are crossing the railway tracks as well as a flyover there, overbridge, road overbridge, not flyover. So these are the, other three bridges here. And of course, there is no suspension bridge in Goa. So now let us first talk about a little bit about the difference of these two bridges, the cable bridges. This is the suspension cable stay bridge, cable bridge. This is, of course, everyone knows which bridge is this. Yeah? This is the Golden Gate Bridge. Yeah. So here the main difference is, here you can see the cable which are taken up there, then it's going down, then some more cables hanging which are vertical. So this is the suspension. So those vertical cables are holding the deck. And the load is getting transferred, the vertical load, the entire vertical load from this is going to the pylon there, and through that it is going below to the ground. And the cable, if you look at the cable size, here, this is the cable, okay? They kept one model there, and not model, actual thing, they have just kept it there near the bridge. for the public to see. And this cable itself is, 3 feet in diameter. So it's huge. And our cable, what you are seeing in Zuari or Mandovi, those are hardly maybe 27 centimeter, 30 centimeter, it's like that. So this is 3 times more. And all this, they make it with small, wires, small wires here, with lots of wires. Some 7,200 something wires are there inside this. So this is the main difference, and also the loading part, how it works. You can see the cables stay, the cables are always in tension, okay? And the deck is in compression. Also, the pylons are in compression. Whereas here, if you see only this cables, of course, all cables are in tension, and the vertical loads are going down there. So there is no compression on the deck in the suspension bridge. So if I just want to show you what is, I think everyone knows what is compression, what is tension, right? So I'll just show you what it is, okay, with a very small thing. See, this is a rubber band, right? So if you pull it, so it is in tension, yeah? So it is trying to go back, basically, always. As long as this tensile force is here, and this being a rubber band, if you hold it like this for maybe 2 hours, it will start losing that property. So all our cables are tension, okay, which is holding the entire thing, the deck. But that, because of the material property of those cables, the high tensile cables, it just doesn't come back within, 1 hour or so. It will be there for 100 years or more than 100 years. So for that, there are certain tests what we do to, make it certain that nothing will happen to my cable. It'll give me service for 100 years and more. Okay. So now let's. So, and more than anything else, all these big structures have some visionaries who initially visualized maybe 10 years ahead of the construction, then a lot of other things comes, and finally it is done. So I will just tell you one story. That is nothing to do with this, our Zuari Bridge, but the suspension bridge, the photograph I showed you of the Golden Gate Bridge. So how they made it, see, this is, there are the men, these 2 men, because of whom the bridge could start. So it was done in 1933, they started the bridge, but before that, about 10 years, they were trying to get it done. So initially what happened, everybody was against it. First thing is, there was a big lobby of this ferry, who were operating the ferry. So their business will go, obviously, once the bridge comes. So because of that, there were some 2,000 lawsuits. Like, things like that keep happening here also. But the engineer, the chief engineer, Mr. Strauss, Joseph Strauss, so he was always behind the government and others for the sanction of this project. So finally, he got it sanctioned in 1930. Then what happened? Then the depression started in US. So there was no one to fund the bridge. So he was looking here and there. Then finally he went to the founder of Bank of America. And he was also one of the person there who also wanted that area to prosper, So both of them had this vision, this area should prosper, we need a bridge. And at that point, the AP Gilani, so he asked only one question to the engineer, chief engineer. He asked, how long the bridge will last? And you look at his answer, he said, forever, if cared for, it should have life without end. And of course, they are always maintaining the bridges. And even now, after 90 years, this is serving properly. And those days, when he did this bridge, it was 6-lane bridge. So when we started Zuari, a lot of people were asking, why 8-lane bridge? Why do you need it? Because so far it was only 2 lanes. But here also, our that time chief minister, late Manohar Parrikar, he was always, I'm looking at the things which will be serving the nation, our state or nation, whatever you call it, for a longer period. So because of his vision, like this 2 person there, this bridge could materialize finally. So I will start with the background. Background you already know, you must have traveled on the old bridge also, most of you, and you know how much difficult it was. And that bridge, of course, for the people with a car, it was okay, but for a truck and other thing, they couldn't even travel because the capacity was low, the bridge capacity. So then as I told you, Chief Minister Manohar Parrikar, so this bridge, the project started, the initial part. Then the important features of this bridge, so it was in January 2016 itself, it was declared and the contract was awarded. Then from 11th of April 2016, the bridge work started. The contract was started from that day. And originally it was only for 3 years, the project period, but it went up to September 23, so almost 7 years. In this, there were some technical difficulties also during the process of construction. Plus the COVID was also a big thing for that. Also a lot of things got delayed. And so for this bridge, this is a combine of steel and concrete. The superstructure is of steel and concrete. So for which they had to fabricate a lot of steel girders, which were of some 10,500 ton. So for that, one factory was also set up there, and these works were done. And at that time, when this bridge was done, so it was the second longest cable-stayed bridge in India. Now, of course, there are so many more in this last few years. And there was a lot of problems while doing it. Like this foundation size, the foundation was huge. It was 89 meters by 27 meters by 4 meter depth. So in that huge area, there were a lot of variation in the soil strata. So when we started the work, of course, initially we did some soil investigation, but being such a huge area, maybe the investigation should have been done at more locations. Because of that, at that point, we couldn't visualize how this strata change will happen, and then again, design has to be changed, So while they were boring, so then suddenly we found, no, this will not work. Whatever design we have done, we'll need some more. So it was again soil investigation done. So that added to the time frame. Then the bridge was designed in France, and also the proof consultant for this bridge was from China. So they were supposed to be here during the erection of the girders when we were doing it. So you need to do, because at the time of erection, I will show you the details, bridge is always in an unbalanced condition. So for that, every day he has to, do some calculation and tell how much force has to be given this way. Like that, so which was not happening because those people were not here. So during that COVID-19. So then subsequently, we were working as authorities engineer for the government. So finally, the contractor, they said, you are here, so why don't you do it? So we said, okay, we'll try. Until that time, nobody in India were doing this exercise. Everything was always done from abroad. So what happened, we stepped in at that point and could, because we could work, immediately we could give the details, what needs to be done next. So we could save a lot of time at that stage. So these were some difficulties during execution. So these are the backgrounds. Now, one second. Okay, no. I should go that side. Yeah. So I will tell, in a very short, because there are so many things I need to explain. So the total length of the bridge is, the main span, the central span is 360 and 140 and 140 on either side. So this is 640 meters, the total length. And this costed some 545 crores. with very little escalation, some 2 crores extra because they had to do something extra which was not in the contract. And then we go, yeah. Then this is what I was talking that time to somebody here, some gentleman. This bridge, when initially it was thought of, that time these towers were already under consideration. This towers has to come. And when this proposal went to the ministry in Delhi for the sanction of the project, so they said, no, we cannot give you money for this, because this is a huge money again. Maybe almost half the cost of the bridge itself for these 2 towers. So they said, no, this is because the Goa government is going to earn the revenue from this, so we are not going to fund it. But you can do one thing, you can, while designing this bridge, since you have already taken these things into consideration, so your foundations you should design in such a way so that all these loads, extra load, whatever is coming from these towers, should be taken care of. So that in future, they can just, whoever comes or whoever funds, they can come and build this on the same foundation. So that's how the foundation were very big here. So now let's come to the main bridge foundation here, what we did. See here, both the foundation, what you were seeing in the photograph, the first one is on the, your Madgaon side, and the bottom one is on the Panjim side. So these 2 huge, from this thing, the pile cap, what you were seeing, so it is almost half the size of a football ground. So it is 89.8 meters lengthwise, 27 meter, widthwise, and the height is also 4 meters there. So it's a huge amount of concrete there. And before that, we had to do this piling there. So in this, the total number of piles, the original design had 70. Then, as I told you, because of this variation of the depth of the strata, so we had to add another 8 piles there in between. So that's how it became 78 piles, and these pile caps. And if you notice there, see the pile caps also we couldn't do at one go, the entire thing. Well, otherwise we'd have to again wait for this whole thing to get complete. That is one thing. And also it will be a huge volume, about 10,000 cubic meters at one go, which is also, it's possible, it's not that it's not possible, but it was easier to do it in 3 parts. So we did it, those were the changes we made during construction. Then this is the drawing of that, so you can see, these are some 14, there are 5 rows, these are 5 piles like this, and there are 14 rows this way. And in between we had this 4 piles, 4 here and 4 here, which we added later. So making it to 78 piles. And these are also huge piles of 2 meter dia, each one is 2 meters. So, yes.
Piles is like pillars.
Yes, it is pillar, but inside the ground for the foundation, vertical. So now these things also, when we need to ascertain what is the capacity of each pile. Of course, while doing the soil investigation, we know the soil strata. And depending on the soil strata, say if bottom there is raw, then of course the end-bearing pile we call it, so that will take the load, the majority of the load. Then sometime we also design it as a friction pile and end-bearing combined, So here it was like that. It was the friction as well as the end bearing in this. So in this we need to again ascertain whatever from the soil investigation data we have. Of course, we could calculate what will be the friction, how much load it will resist, and from bottom also. So there is certain loads. If this much is the capacity, that way we decided it will be 70 piles initially. But then we need to confirm it by doing a test. And this was one test which was done. This is normally in bridges where the piles are smaller than 2 meters, up to 1.5 meter. We just load it with a platform, we put loads there, then we put a jack on top of the pile, then we give the load on the jack. So jack starts lifting, lifting the your platform. So in turn, the load gets transferred to the ground, and that's how we used to do. But this is a different kind of mechanism. Here, the jacks are, put inside the pile. There are 4 jacks of 900-ton capacity, and this was our test pile, which is not in our main working area. This was a little away. So this thing was done, but I mean, everything, you have to do the concreting. Everything is inside, buried inside. Then, for whatever reason, maybe the electrical line got cut during concreting, this whole test failed. So we couldn't get any, result from this test. So then we had to go for a, prototype test. So that is also allowed with our, codal provision. So we did that in a smaller pile outside, not inside the river, in a similar soil strata, and that was interpolated to get what will be the capacity of this 2-meter dia pile. Okay. Is it becoming too technical now? Little bit. Yeah. Okay. Then I will go a little differently. And this is also technical, but what happens when you do such huge concrete which is 4-meter depth. So inside, once you mix the concrete with water, then you pour it, then you start curing it, then heat of hydration develops. And because of that heat of hydration only, the concrete sets. So you must have seen while traveling, any building or anywhere, after doing concrete, they put some clothes, Hessian clothes and some water, so that they can control that heat of hydration. But here it was inside, this is 4 meters. So whatever I do up here, so inside it's not helping to reduce that temperature, So for that, we had to, these were not original, in our original thought. You will have to provide this sort of piping through which will be, pumping. We had one, here you can see, this was from here, everything was there, all this ice cool water. So this was pumped so that the concrete becomes cooler, and that thing doesn't happen, that heat of hydration, the difference of temperature we can reduce basically to avoid cracks in concrete. And this concrete also, it comes in different grades. Here, these were all in very high grades. And this was the mixture, the things what we added to make that kind of concrete, high strength concrete. And since we did it in 3 parts, finally we had to, originally it was not there in the design, to put some cables here to make it, monolithic kind of thing. So that was also done, which came later. Then I will just show you some pictures. So this was, initially we started piling. Then you can see the first part of even the pylon, this pile cap is done, even the pylon is starting. Then pile cap, again we are getting it ready for the next, and here pilings are done. And here also from the other side, the last part of the pile cap. Then here it is ready for concreting now. And all these concretings were done through some pipelines. Everything was at the bank of the river, so which were pumped from there right into this. Then while doing, all this work at site, we had the huge things to be done, the superstructure and steel. So for that, we had to set up one fabrication yard near the site, and we'll just talk about that quickly. So this was the facilities what was created there. So this is about 10,400 square meter of area with some, some major machineries like this, for cutting, then the drilling, then welding, all kind of these machineries were all inside there, just adjacent to the site. This was the interior of the factory. There's another image. All these steel plates are, kept there. And then this was the floor plan. From one side, the material used to come, and after all this thing, right from cutting, drilling, then welding, it used to come out. Then it was again salt blasted. Those I will show you the photographs. Then these are different kind of plates what we use, different thickness and different grade. Then this is the cutting machine. So this machine also used to work with a computerized, the drawing they used to convert the drawing to a, something called with another software called MOS T2D. So with this, they used to decide, the machine used to decide how to cut the plate so that we can optimize on, minimize on your wastage of the steel. And this is the drilling machine. And this is the, the welding machine through which you can see the beam is coming through this, and welding keeps happening here on from both sides. Yeah, it moves through this, and these are the nozzles where this welding happens. This is another kind of welding machine. This is robotic, it can turn, move in different directions. And this is another machine. Because of this heat, when we are welding, the steel warps, it bends. To correct those things, the entire beam has to pass through this. Next image you will see. See here the beam is coming here through this. Then of course the welding, with those things, with the steel elements, we had to weld some studs, because finally it has to go inside the concrete, so that the bond between concrete and steel is there, the main structure. All the studs are welded. And this is, whilst in the start, there is something called ceramic ferrule. So this, what happened, this point here you were seeing, so that melts. And also the the material of that beam, or wherever you are connecting, that also melts. But during melting, this just protects that area, so that it can fuse easily. And this is the shot blasting happening here inside a closed chamber. So we put some small metal shots. It is with a very high pressure, it is put there so that all the scaling and little bit of rust, everything comes out. Then you see, this is, after the shot blasting is done, even the color has changed of the steel. Then we apply this different coats, the protective coats here. Then this is the last coating, this is metallizing. So here this wire is getting melted there, and it is with some this air pressure, it is just applied as a paint there. Now this is the pylon, as you have seen, always seeing in the bridge. So I will just go quickly, okay? I will not explain too much of technical thing. This was done in 3 parts. This is the bottom part. This is, we call it pedestal. Then this is the lower pylon. From this, after the pedestal, up to that tie beam level. There is a tie beam that is at 50-meter level. So up to then, it is the lower pylon. Then it goes up. No, this is also, I am just showing the formwork of the pylon. Then here is the beam. Okay, and by the time you come up to this beam level, because these 2 legs are inclined, so there is all chances of them coming closer at the top, Because of that, before we start, doing this concreting, we put a jack here. We do 2 parts on both sides. Then with a jack, hydraulic jack, we just, give force so that whatever correction we need to do before we go further, because we have to go another 50 meters above this level. So we correct those things, and then we finish this entire concrete and further go ahead, top. So this is, you were seeing those cables when you travel at the top, also you were seeing the cables coming down. You see only this yellow part, right? So each cable, inside there is a huge steel frame where all these cables are anchored inside here. And those are also, stressing is also done from inside, because entire this pylon is hollow, From outside you cannot really make out whether hollow or, solid. Yeah. And the concreting, as I told you, up to this 50-meter level, this level, was all done by pipe, this pumps, hydraulic pumps. Above that, it was all with this, bucket, which were lifted through this crane, and with some 2 cubic meter capacity buckets. Because these were all small lifts, 3 meters at one go we were doing. And these are some photographs during the pylon construction. was in the evening, after sunset. This was a factory. This is the factory, which was very close. This was also at night, late night. These are during day. Then we come to the superstructure. Okay, we are now building the superstructure. Also, the elements are in the fabrication yard. Inside the factory. And now I will just talk about the superstructure a little bit. This is you cannot. When you travel, if you look at the bridge from the side, you really cannot make out that the beam is so high. This is 2 meters high. You can see the man there. There is space up there. So, and this is only a small part, the footpath area where in the bridge there is a footpath section. This is only for the footpath section, where the total width is 27 meters here. And these are all where in total some 92, were done, segments were done. Of the 106 in total, 92 were with a very regular dimension, which is 12 meter, 27 meter. And some of them were with little, different dimension to make it, to bring it to the correct length. So this 106 segments, and each was about 100 ton. So that much of fabrication work was done there. And yeah, these are the drawings of that section. And also another important thing, another test we need to do for this kind of, high-level bridges or the long span bridges is the wind tunnel test. So you must be very much aware about that, being in aviation. So this was done in CSI or SCRC in Chennai. So here, what they do, they have a huge tunnel. This is the tunnel. You can see what you are seeing is a tunnel closed, through which they blow the water with a huge, fan at the back, at different angles on your structure. And they just, they have so many sensors here. From the sensor, they know how much of these things will move and other things. Finally, while designing, we have to design it for some, drag coefficient and things like that. Those things are there. So fine, whatever we assume, while doing initially we do the design. That time we assume something depending on because each area, what is the air, the velocity and all this thing, we already know, wind velocity. So based on that, we do it, but we need to again confirm, depending on my section, what is the section of my bridge. So these tests are done. And here in this bridge, when you travel, if you notice one thing, the crash barrier, on Mandovi Bridge, you have seen those are all with, concrete crash barrier. So this bridge also originally was designed with concrete crash barrier. But when they did this test, they said, no, that will create a lot of extra, force there. So better you make it open. So they are only in the beginning, maybe 35 or 40 meters, they have allowed us to do this concrete. Then rest is all steel. It's open, so that air could pass through. And all this, the bridge, the main part, the main part means whatever this cable part, all were procured from China, all these things. And luckily we could procure it before COVID. Before COVID itself, we purchased everything. Everything came here. Otherwise it would have been another problem, for the material. So this is the factory where all these strands were made. Okay, I will just show you now. These are the strands, which are inside those yellow. Whatever you see is the yellow cable, but inside these cables are there. These are the strands which are inside those cables. I'll show you where. And this is another factory from where all this anchorage is. Where you finally, lock those cables at the end. These are the anchorages. And again, for this also, you have to do some test for all these cables. So this cable and this test with this higher number of the strands, because here the total load on the cables are much higher. So this test, there is no facility in India to do this. you can do it only with maybe 1 or 2 strands. As I told you, this is the anchorage where these cables are fixed with some wedges here on this strand. These are the strands. So this particular test, which was the lowest size of cable, which had 37 strands, so this was tested in China. They had a facility there. So, and these are the things, this is tested for 2 million cycle. That means what happens, like I showed you in this thing, it'll just keep on moving like this for 2 million cycle. And in that, what is the breakage and all this thing. But that too, here we are going up to 95% of the ultimate tensile stress of this. That is a property for this steel, okay? Up to that we go, then, but the total, while designing this sort of bridge, they allow you to go only up to 45%. So you can imagine, so much of margin is there. So even in that bridge, if say for whatever reason some accident occurs, one cable snaps, nothing will happen to the bridge. Okay, because then whatever the load, automatically, say one cable gone means whatever load in this area will get transferred to the next one, which is still capable, which we have stressed only up to 45% of its, ultimate strength. So that is one reason why, this sort of bridge, they allow you to do only up to that. Because other things like, say, a beam, what you see in normal bridge, there we can go up to 75 or 80%. Okay, they allow. But in this case, it is only 45%. So similarly, for the bigger cables, again we have to go right up to US for testing those cables. So those facilities are not in India, but I think they should start getting those facilities done here, so that it costs a lot of money. So many people, maybe 5-6 people go there for 3-4 days, coming, going and staying, a lot of money. So this is again the other two, which were...
Pieces of cable are tested.
Huh?
You take the cable to be tested?
Yes. Not the full cable, only a part. So this you are saying, maybe this is 20 feet or so. This part and this anchorage, because the failure happens here in the anchor. Okay, mostly in this area, because there the concentration of force is maximum. So here, for our case, there was no problem. It allows a breakage of, it should be less than 9. It can break, but breaking means failure has started. Okay, but in our case, it was nil. So this erection, I will just go show you the pictures now. Okay. See, these are the steel frames which came, you bring it there and put it initially on some support, because you have the pile cap there. Okay. Then we start putting all these slabs. So these slabs are also, it looks small, but these are, you can see, this is 10.2 ton one, the biggest one. Then there are some smaller ones. This is in the footpath area. So here it is little less. Then our factory was here. So from factory, how they take it inside. Then, you take it there, then you start lifting. Yeah, this is the lifting, how it's happening. Then, you keep connecting those after lifting. Then all the slabs comes. Then you finally stitch all of them to make it look uniform, that everything is kind of. And this is what I was talking about, this Chinese and French people who couldn't come. So here, this is the procedure through which we keep lifting, one by one after another we have to do. And every time you lift one unit here and connect, we need to, take the we need to observe all the levels and everything, levels, and also the force. Because it's being in a cantilever here, it always, one thing is it always tries to droop below, so that, you have to correct it before the next segment comes. So after doing the survey, we tell the designer, in our case, which was in France, but he couldn't respond because of COVID. So it was done here, and the designer will again tell you, no, you have to, this cable you need to stress a little more, then only it will come up. And there was a big kind of, I'll say it was a mistake. Every time we used to add, whatever it is designed, it comes, it tells you that this much should be your deflection. But we were getting always higher deflection. We think, why it's happening? We used to shout at the French designer. Initially they were doing, they don't even know what design they are doing, what is wrong. But the wrong, what happened, all this, precast thing. Normally what happens, whenever in a concrete, we calculate what is the weight. We take the, the volume and we multiply by 2.5, 2.6 within that range. But in this, there was so much of steel inside, it was much higher. So because of that, the load coming was much higher. So he is designing it for a lesser load. And, then how we came to know, we had some doubt, maybe this may be the only reason. So we took them and we started weighing them, few of them. We said, it's because of that. Then we could correct that, with that. So many things, it happens, but, during the execution, you need to be a little cautious why it's happening, then you can correct it.
You mentioned stitching between the segments. What
No,
do you mean by that?
stitching between them. That's a concrete, basically. Stitching, this is a stitching concrete. This slabs, there are gaps here. So this will have to fill with concrete. So then this is our model, in the Midas, in a software, we put all this, deflection, our load on the cable. So that shows us how the structure is at that moment with those things. Then they will correct and tell us, no, you have to increase the load there or whatever. And accordingly, we'll have to do before the next segment. Now here also, you see, everything is happening. Can you notice this side is little up, then this side is down? Yeah, so but finally we have to make it in same level, right? This is the last segment which is coming up. And here it was much easier to do because of this load, here of this frame. This is the temporary thing. It was a lifting purpose thing. So we shifted, we brought this one forward, this one little backward, okay? So that balance, then we lifted it and bolted it.
Yeah, people were talking when they saw that at the last stage.
Then these are the bolting, what they do. I'll go quick, there's no time. And these are the, those yellow, whatever you see of those cables. So this also comes in certain size, then they weld it there, at side depending whatever the length you need. So it is done, they cut it, they heat it up, then they weld it hydraulically, they press it, it gets welded. Then this was the first cable, what they were, not cable actually, only the outer cover, they were sheathing, they were lifting. Then this was from this, at the top, the cable, all the strands are lifted, put it in that machine up there, they coil it. Then one by one, they put it through the tube, which comes down at the deck level where it is connected. So this it comes here. On the right hand side, you see, this is at the deck level. So this is the fixed end, then this is the top end, stressing end. This is inside the pylon. And even now I can go there inside. There are some steps, ladders there, so we can go and inspect how things are. And these are of course, this is too much of technical details, so I will just skip this. And you see, I was telling you, so every time after putting all this stressing, he is again taking the levels, So whether this side is down, up, so that for the next segment, we need to correct it beforehand. These are the machinery with which we stress. Then this, I was telling you, the stitching. All this, those slabs, which were in precast slabs, are all connected now. And this is the last span. So here what happens, this bridge, as I told you, this central span is 360 meters, end spans are 140. So it is 360, half of 360 is 180. So this side is smaller. But all these cables, the cable cannot be less this side. Everything has to come this side also. So here you can see all these cables are at a very close distance. And we need some more extra dead load in this side. Because of that, this part was not with this kind of segment, it was filled with concrete to give that extra load there, so that it's balanced. And here, this is the back, so here they are doing this, for the cast in situ concrete. Then this is the reinforcement there. Then one more thing happens because of that imbalance, So we need to put some tie beams, some cables here at the end. Okay, this is they call it anchor pier, where I am anchoring this entire the cable structure, because this is the end of the cable structure. So here I am anchoring the whole thing. Basically, it's anything. Otherwise it may try to lift, sometime because of the loading. So it's there. Then this is the expansion joint, and that bridge has only two joints, one at the both end, that 640 meters apart. Then some picture of this superstructure when we were launching. I'll quickly go. Yeah. Can you find something missing here in this picture?
In the middle part?
No, that is of course of the bridge. I'm building something else. Something else is missing. No, there is no pillar. This is 360 meter from here to here. Yeah, you said something.
Existing bridge.
Correct. Those are not here. Yes. Now I just removed it so that otherwise the view gets, here you get a clearer view. Yeah, here you can see the existing bridge. It's there. That is when you come down from the airport, from this road. Yeah, this is the up ramp. Straight you go to Madgaon. Now it was almost closing down. And then the bridge on both sides, it rests on some bearings through which also the load get transferred from the cable, from the pylon it's getting transferred directly also. But part of this, whatever is resting here in this part, on the on your pile cap area, there it rests. Now we are almost to the end, okay? So here the lighting is very basic at this moment. But once this tower comes, along with the tower, so they are going to do, lighting like Mandovi or maybe better than this. So that will come later. So this is the regular street light is there. Then this is very important thing. Once you complete a bridge, any bridge, in fact, you have to do this. This is the load test. You have to see whether the bridge is really behaving the way you want to, way you have designed it to behave. So this is the drawing, of course, for the loading. Better you look at the picture. So here you can see there were some, 32 trucks. Each truck was 32 tons. So about 1,024 tons was at the center. It was put in stages, of course. From say 25% loading, then hold it like that, then take the level, then go to the next. And before we did the test, what we have calculated and we found, at the center, the bridge can sag by 500 millimeter, 50 centimeter, okay? But the main thing is, how much it sags is one thing, but how much it comes back, that gives the, the elasticity of the material, that it can come back, that is required. If it cannot come back, means it failed. Then you have to discard the bridge. Really, say you just take a plastic thing, hard plastic, you bend it, it just cracks, okay? When it is elastic, it will bend, but it will not crack, it will not fail, okay? So that's what is the test for. So, and we got, our deflection was 422 millimeter, okay? And it came back, minimum 75% rebound should be there as per code, and we got 92.95%, so it is okay. So that is why whenever you are on a bridge, any bridge, say with a longer span, you are standing on the footpath, some huge truck or something goes, it vibrates. So you shouldn't feel worried.
Even in the car.
Yeah, so it should, no, sometimes people think, it's vibrating, something wrong. But it should vibrate. If it doesn't vibrate, someday it may fail, and without giving any warning. So this is the completed bridge, but now it will look better because this painting of the bridge was not in the original contract. Now they started, then again they stopped because of the rain. So now again they will, from the next month, they're going to start and complete. Now I think this part is complete, 2 or 3 legs, only the outer legs are complete. So from the project, we learned few things. So one is that the factory at site, which is very important because that way you can control both, time and quality, everything you can control. And the contract should always specify for huge foundations, it should specify, because normally our thing is, it's a kind of a basic thing. Each foundation will take one borehole and see. But for a bigger one, they should say, this is this much, defining the area, this is the area, then you should go for 10, 5, 4, whatever. Then this construction stage analysis, of course, it should be always done inside. Then we have also used this GGBS in place of, cement, which again reduces this heat of hydration. So, and also the price, price of this GGBS is also less, and it gives you much higher strength of concrete. So these are the things, and yeah, thank you.